Today we're going to talk about AVR communication through a peripheral called USART. This is another important feature of microcontrollers, which is the ability to communicate with other devices. Here we have an example where we are communicating with another microcontroller, but we also have the possibility to communicate with other devices such as a personal computer. To do this, the microcontroller has a peripheral called USART0, which stands for Universal Synchronous and Asynchronous Serial Receiver and Transmitter. The main features of this peripheral are the full duplex operation, which means that it can receive and transmit information at the same time. It can operate asynchronous or synchronously, which basically means that you're going to have a TX pin, which means that you're going to transmit information. You're going to have also an RX pin in which you're going to receive information. For asynchronous operation, that is all you need. However, you can also have an external clock pin, and this pin can be either output or input, and this is what it's going to give us the synchronization. Another thing is that it has a high resolution baud rate generator, and we can send information in various ways. That is why it's called universal, because it can send 5, 6, 7, 8, or 9 data bits. It can send 1 or 2 stub bits. It can generate parity with either odd parity or even parity, and also it can check parity by hardware. Also, it has a mode that it's 2 times the speed in asynchronous, and more importantly, it can generate 3 interrupt sources. When it finishes transmitting, which is the TX complete, the receive complete, and once the transmit register is emptied, it can also generate another interruption. We will review its characteristic and setup. Let's review the USART0 register structure. First, we have the data, and the data, we have a register that is called UDR0, which is from USART data register. And of course, the 0 is because some microcontrollers have multiple USARTs. However, this register is 8 bits, but we said that this peripheral can send up to 9 bits of data. So we have another bit somewhere, it's bit number 8. In order to receive information, we need an external pin. This external pin is called RxD. Notice the direction of the arrow, that it's going towards the UDR0. This means that when we receive information, this information is stored in UDR0. However, we can also send information. And when we send information, the interesting thing is that the data is also coming from UDR0. So when you send information, it goes from UDR0 and it goes to the transmit pin, which is TXD. How does the microcontroller does this? Well, basically UDR0 has 2 locations. One location for transmitting, it has another location for receiving. If it receives information, it stores it in this location, but if you're going to transmit information, you need to store it in this location. However, both locations are named UDR0. So how does the microcontroller knows if you want to receive or if you want to transmit information? If you send information to UDR, it means that you want to transmit it. However, if you read UDR0, it knows that you want to read the information that you have received. Next, we have the velocity or the speed. The speed of transmission is determined by a setting that is called baud rate. This baud rate has 2 registers. Both of them are called UVR-R0, but one is the high part and another one is the low part. With these 2 registers, we can generate the speed in which the microcontroller is going to send information. However, since we said that we can also have synchronization, we also have an external pin. This pin is going to help us to synchronize the transmission. And this is why it's called full duplex, because you can be receiving information and at the same time be sending information. Now let's talk about the 3 configuration and status registers: USART0A, USART0B, USART0Z. So here's where the extra bit is stored in USART0B. Another thing that we have is the error detection. We will talk later about error detection. We also have a configuration that sets the double speed. And we also have another configuration in USART0A, which is the multiprocessor mode. In USART0B, we have the receive enable and the transmit enable. This is very important because if you do not enable these 2 particular bits, even if you say you want to receive information and you start receiving information, then the microcontroller is going to ignore what you are receiving. At the same time, if you say you want to send information, but you do not enable this, even if you write to UDR0, the information is not going to be sent. So these are two very important bits that you need to remember. Another important part of configuration is the character size. The character size determines whether you want to send 5, 6, 7, 8, or 9 bits of information. UCS means USART character size, or we can say char size. So it's USART char size bits 00 through 02. Another thing we have is the mode select. This is configured by 2 bits, which are called UMCell01 and UMCell00. When you have 00 in these 2 particular bits, you're going to have the asynchronous mode of operation, which is the most used in our serial peripheral. Also, you have the parity mode. The parity mode, you have 2 bits, the USART parity mode 01 and USART parity mode 00. With these 2 bits, you can define whether you want to check parity or you do not want to check parity. We're going to talk about what parity is. Another configuration is the stop bits. You have 1 bit to determine the number of stop bits that you're going to have in your transmission. You can have either 1 stop bit or you can have 2 stop bits. Getting back to USART0B, in this particular register you can enable the 3 interruptions that we talk about. You have RxCIE0, which stands for receive complete interrupt enable 0. You have TXZI0, which stands for transmit complete interrupt enable 0, and you have UDR-EE0, which stands for USART data register interrupt enable 0. When you have interruptions, you can also have the status flags. So for these particular 3 interruptions, you have the 3 status flags of these interruptions. So when you have a reception completed, you're going to have a 1 here. When you have a transmission completed, you're going to have a 1 here. And when the USART data register, when this register is empty, this is going to become 1. Now let's see a little about the USART block diagram. There's a lot of information here to process. However, what I want you to check is just that, first of all, you have 2 locations which are called UDR. So you have here, which is the UDR for transmission, and you have here the UDR for reception. If you write info to UDR, it's going to go to this location. But if you want to read UDR, then the information from this particular location is going to be read. Another thing that you need to understand is that we have something that is called the transmit shift register, and we also have something that is called the receive shift register. When you want to transmit data, you put here the information, and this is what you want to transmit. But once you transmit it, or when you start transmitting, all this info, it's going to go into this transmit shift register, thus releasing the UDR register. The UDR register, it's going to be emptied, and this information that you send to the UDR transmit register, it's going to be put inside the transmit shift register. This means that you have something that is called a 2-character buffer, because you can send information to UDR, and as soon as it gets to UDR, it's going to be moved to the transmit shift register. So you can write another character to UDR. Here the transmit shift register is going to be connected to the TX pin. On the reception part of this USART, you have the reception pin here, and this reception pin it's going to start telling the microcontroller what information it's going to be receiving. So when it starts receiving information, it's going to start receiving here the first, the first information, then it's going to receive the second information, so this information is going to be shifted to this place until at the end of the cycle, which is 8, or well, whatever information you have, and then you're going to have the reception complete. And when you have the reception complete, this information is going to be stored, or it's going to be copied to the bottom part, and it's going to go to the UDR register. However, if you take a close look, once you are receiving information, the temporary data is going to be stored in this particular register. And once you complete the reception, it's going to put this information into this location. So that means that you can start receiving a second data, and it's going to start using this information, this register, And once you complete this information, it's going to be stored in this particular location. So this means that you have a 3-character buffer for reception. That means that you can read up to 3 characters in the reception queue and still be able to function. However, if you do not attend this information, if you do not read this information, then of course the buffer is going to be full. So one thing that is very important is once that you have this information, you want to read it, because once you read it, you're going to release the buffer. So how the information is sent and received to UDR. So well, this is the frame format, and basically you have here how the information is sent or received to the reception pin or transmission pin. Over here you have the voltage, and in this axis you have the time. So this is what the frame is. And when you have high voltage, it means that the transmitter is idle. After you're idle and you have low voltage, then it means that you're going to start transmission. This is what this means, is you're going to start transmitting or receiving information. Then you have the possibility to send from 5 to 9 bits. So you have this is the information if you send 5 bits, 6 bits, 7, 8, and 9 bits. So you can send either from here or to here of information. This is the information. Then you can choose to select parity. And that is why you have parity between brackets, because this means that this is optional, because you can choose to not generate parity. Then you have the stop bit, and the stop bit you can choose to send either 1 bit or 2 bits to tell the other device that you have stopped sending information. And you have the option to either start a new data or remain idle. What happens if you want to send or receive information? This applies for both cases, for both scenarios. If you want to send 0xF0 and you want to send it with 8 bits, you want to send it with even parity, and you want to send it with 1 stop bit. You always are going to start at idle. This means that there's no reception or no transmission. When you want to start sending or receiving information, you're going to start with a low bit. And this low bit has to have a specific duration. This time it's going to be determined by the BAUD rate. This is going to depend on the speed of the transmitter. If you have greater speeds, of course you're going to have lesser time. This time, of course, is going to be repeated throughout this example. And again, this is the same time as this one here. And this is how the microcontroller is going to know when to read information. You are always going to start with the least significant bit. This meant idle. Then you're going to have a start here. After this time, after this particular time, you're going to start sending the information, and the information is 0xF0. And 0xF0 is in binary, and you're going to start with the least significant bit. So this least significant bit, it's going to be the first one to be sent. So this means that you're sending a 0. Then of course you're going to start sending the other 3 zeros. And then of course, in this particular time, you're going to change to send this particular one. So over here you're going to go up to the 5 voltage, and this is going to mean that you have a 1 of information. And of course you can see that all the 3 remaining bits are also 1. So then at the end you're going to send the parity and the stop bit. So here we're choosing to actually send the parity. So the parity means that we're going to count the number of ones. So I ask you, what is the number of ones? You have 1, 2, 3, and 4 ones. So the number of ones is 4. So the number 4, is it odd or is it even? And the answer, of course, it's even. You have an even number of ones. You have 4 ones. Since you're sending even parity, that means that you want to tell the other device that you have an even number of ones. So for yes, if you have even number of parities, for yes, you're going to send a 0. 0 means I do have even number of ones. Okay, so we're going to send the parity, and we're going to send a 0. Then I want to send the stop bit. and the stop bit it's a 1. And then after this, you can either go low or you can remain at high. If you remain at high, you're going to remain idle, and if you send a low, you're going to start a new bit. That is what the frame looks like in serial transmission. Let's see another example. What if you want to send 0x30 with 7 bits, odd parity, and 2 stop bits? First, you're going to start idle, then you're going to start the information. Then, since you want to send 3 bits, 0x3a, it's that. Again, you're going to start with the least significant bit. You're going to start with a 0. So you have 1, 2, 3, 4, 5, 6, 7 bits. That would be the information sent through the pins. Then you have odd parity. So odd parity means that you want to count the number of ones. So you have 1, 2, 3, 4, 5 ones. So you have the number of ones, it's 5. So again, you ask the question, is it odd? The number, is it odd? And the answer, of course, is yes. And since it's yes, you need to send a 0 again. A 0 means yes. So I do have an odd number of ones. If this was an even parity, of course, if this was an even parity, you would ask, do I have an even number of ones? And the answer would be no. And since the answer is no, you would put a 1. So the parity, it's going to go to 0. And then you have 2 stop bits. So this means that you need to wait at least 2 transmission cycles to say, I have stopped. Let's use this example to talk a little about error checking. If we want to check errors, we have 2 things. First of all, we can check errors with this particular bit. If this bit is 0 and you receive information and you calculate this bit, this is the important part, you're going to receive this bit. This bit, it's real. But you also need to calculate this bit using the information that you receive. And if the bit, which is 0, it's different than the calculated bit, then you're going to have an error. This is one possibility of error, when the parity does not match. And the other one is if you do not receive the stop bit. If you do not receive the stop bit, this means that something has happened. You have some error that it's called a frame error. Because remember, this is a frame. This is a frame of information, and if you do not receive the stop bit correctly, it means that somehow the frame was not constructed correctly. Now let's talk about the USART configuration. And if you remember on the previous examples, we said that we have something that was called the BAUD rate. So the BAUD rate means that we are going to calculate the speed in which we want the microcontroller to transmit. So for instance, you can say I want the BAUD to be 9,600 bits per second. And you can calculate the value of the register that is called UVRR, which remember means USART baud rate register. So in order to calculate this, you have 3 options over here. You have the option to go with the normal mode of asynchronous, or you can have also asynchronous, but the double speed mode. And the third choice is that you can have the synchronous master mode. And for these 3 choices, you have different types of calculations. Most of the time you're going to send it with asynchronous, because asynchronous, remember, means that you have a TX pin and you have a receive pin. So you're going to transmit information and you're going to receive information, and that's all you need for asynchronous. If you want to synchronize your 2 devices, then you need a third pin, which is the external clock. Another thing that you can configure with the USART is the selection mode, which remember it's either asynchronous or synchronous, but we actually have a third choice. So we can choose asynchronous with 00 in these 2 bits. We can choose synchronous with 0 and 1, or we can choose master SPI with a third mode. And when you choose this, you can program another microcontroller through USART. Another thing that you can configure is the parity, remember? So if you have 00, which is the default, you have disabled parity. That means that you're not going to send the parity of the information you send. And when you have 1 0, you're going to have it enabled with even. For 1 1, you're going to have odd parity. And another thing that you can configure is the stop bits. So you can either choose 1, which is the default with 0, or you can choose to send 2 bits. And also you can choose the character size, remember, if you want to send either 5, 6, 7, 8, or 9 bits. An interesting thing to notice here is that if you remember, these 2 bits belong into one register, and this one here belongs to the register B of configuration. So one thing to notice is that most of the time you will be talking about these choices. The only time that you need to actually write to the B register is when you want 9 bits of information. If you remember, before we talked about error checking, these checks are performed in USART0A, and we have these particular bits for checking errors. First, we have a bit that is called FE0, and this bit is set when there is not stop bit detected. Remember, this means frame error. So when there is not stop bit detected, we have a frame error. We also have another bit that is called DOR0, which stands for data overrun. So this bit is set when the reception buffer is full. Remember, the reception, we have 2 characters in UDR, and we also have 1 character in the reception shift register. We have an error when we have these 3 spaces full, the 2 over here and the 1 over here, and also we receive an start bit. And we also have another bit that is called UPE0, which stands for USART parity error, which I already explained. These 2 bits, they apply to the next character to be read in UDR0. Remember, you have 2 characters in UDR0 plus 1 character in the transmission shift register. In the reception shift register. So this means that all these 2 bits are only useful before, and this is important, before you read UDR. So if you read UDR0 first, then these 2 bits are lost. Let's see a little example. We will review the asynchronous mode of operation to show how to communicate with another device. Say you want to communicate, and this means that you only want to transmit with another device at 9600 bits per second, in a frame of 8 bits, even parity, and 1 stop bit. So what you want to do is first set the UM cell properly. So that means that you want to put 00, remember, to get asynchronous mode, and actually that is the default operation. You want to configure the frame format, and first you can write these 2 bits, which is usually as 01 and 00 to 3. Then you want to put UPM 001 and UPM 00 to 2 to choose even parity. And finally, you want to put USBS 0 to 0 to put 1 stop bit. Then you want to calculate and load the baud rate. Okay, and for that you're going to use these formulas over here. So first you're going to calculate using the normal speed. So you have the frequency of the microcontroller divided by 16 times the baud rate you want to generate minus 1. This is very similar to the calculations of the timers. So you get 103.166. And for the double speed you have the same, but instead of dividing by 16, you divide by 8. And you get a 207.33. What is the best choice? Do we choose 103 with simple speed, or do we choose 207 with double speed? The answer is it's the same. With both options, you actually achieve a 9615 bits per second. So you do not actually achieve the 9600 you wanted, but that is okay. And finally, you want to enable transmission. Remember, if you calculate and you put all the configuration, but you do not enable transmission, then your microcontroller is not going to transmit the information you send to it. Optional, you can also enable interruptions. In this particular example, we're not going to use interruptions, but you could use interruptions. We want to configure the peripheral. Then we want to make a variable equals to 255. Then we need to wait, and this is a safe way to do it. It's you want to wait until UDR is empty. So if it is empty, you can write information to it. You transmit information by making UDR equal to the variable. Remember, you write information to the UDR. Then you want to decrement the variable. So it starts at 255. So it's going to be 254 for the second iteration of this loop. And you're going to wait 50 milliseconds. So let's see the code. First, you have 2 includes. The second include It's one utility that it's going to allow us to wait 50 milliseconds. For that utility, you want to define this constant, which is the frequency of the microcontroller. Then we're going to define one variable, which is going to be called variable, and we're going to define a function that is going to configure the USART. So the main program is very simple. First, we configure the USART, and then we make the variable 255. This is a while, so you're going to keep checking. You're going to keep checking until UDR0A turns on, because once it turns on, the logical operation with UZR0A it's going to give us 1, but inverted is going to give us 0, so the while is going to be false, and then you can proceed. Then after checking that, you write the variable, so this is the actual transmission. Okay, well, this is the order to start transmitting. Okay, this is not the actual transmission, you are ordering the microcontroller start transmitting. Then you do what we were proposed, decrement the variable, and then wait 50 milliseconds. And finally, that's the way we do the configuration, which is the most important part in this video. We write to UZR0Z, we write the parity we want, and we want the character size we want. And even if we're not writing the stop bit, we know that for default we have a 1 stop bit. Then we write the 103 we calculated, which is the 9600 bit per second, and finally we enable transmission. You can write this program to your Arduino and then use any serial monitoring program to see what happens. Notice how we do not do any error checking since we're only transmitting. This is important. You only do error checking when you are receiving, not when you are transmitting. Thank you very much for watching.